Okay, so today we're going to sort of switch gears, move over from talking about recurrent neural networks and convolutional neural networks and multi-layer perceptrons and all the standard ingredients of a neural network recipe, and move on to somewhat more complicated or a little more sophisticated topics for the day. Today I'm going to be talking about deriving representations from neural networks, or what we'll actually cover today is we'll try to get a little bit of insight into what it is a neural network actually learns at the level of representations. In the next few classes we'll be going over, we'll take a little step back in time and go over Hopfield networks, and then go over Boltzmann machines, and then we'll come back to the business of representations and generative models from derived using neural networks. So today's topic, we're going to look at what a neural network actually tries to learn. So let's begin with the basic problem itself. The basic problem was, here's what learning did. We were given a collection of input-output pairs. We defined some kind of a loss which quantified the error between what the network actually computed at each input and what you wanted the network to compute at each input. You learn the parameters of the network to minimize this loss. So consider this. Now the loss could be anything. The network could be trying to perform some kind of regression. It could be trying to perform classification. We know that it's a universal approximator. It can approximate pretty much any kind of function. Let's specifically consider the problem of classification for the day. So, or at least for the first half of the lecture. So let's say you're given data of this kind. What you would ideally want to learn is a classification function of this nature, which gives you a 0 whenever the input is in the blue regions, and it gives you a 1 whenever the input is in the red regions, to identify if an input happens to be within the yellow region of the picture or not. So now there's something shady about this picture. I gave you these red and blue dots, and I could actually place these nice clean double pentagons around these red and blue dots such that the pentagons exactly enclosed just the red dots, and there were no blue dots in the red region and there were no red dots in the blue region. In reality, what happens? You're going to get something like this. It's going to be fuzzy around the edges. You're going to have, near the edges of this boundary, you're going to have some blue dots in the red regions, some red dots in the blue regions. In fact, it's going to be hard to define what is a blue region and what is a yellow, the red region near the boundaries. And so the image is going to be something more like this. I mean, this is my attempt at trying to draw fuzzy boundaries. It's not very good, but you get the idea, right? So now this is a nonlinear problem. The decision boundaries are not lines. To understand what's going on, let's first sort of simplify this, take a step back and look at the problem of linear decision boundaries. So let's say we wanted all of our data live in some high dimensional space. Let's, for example, 2 dimensions are high for my illustration, say some 2-dimensional space, and the red region is separated from the blue, or in this case, the blue, by a hyperplane. So it's a linear, these are linear decision boundaries. A hyperplane is a linear boundary. So in this case, in the 2-dimensional case, your decision boundary is going to be an exact line. What is the kind of function that you'd actually be trying to learn with your network? A step function of this kind. So that's your decision boundary. The output must be 0 on one side. It must be 1 on the other side. But then you are trying to learn this from training data, and the training data are going to be of this kind. So you have a bunch of red points sitting at a height of 1, and a bunch of blue points sitting on the floor at a height of 0. Except what you will actually get is not something that is so cleanly separated by a line. You're going to get some red points on the blue hanging in space in the so-called blue region, and you're going to get some blue points sitting on the floor in the red region. So if you look at it from the top, you're going to get something of this kind where there's no way of drawing a clear line which separates the red and the blue regions. And this is much more realistic for what you will actually get in life. Now, to understand this, let me take a step back and simplify it further. 2 dimensions are already hard to comprehend. So let's work with 1 dimension. In 1 dimension, the input feature x is going to have only one value. It's a scalar. And the output is going to be either 1 or 0. Now, here's what the training data are going to look like. You're going to have a bunch of red points sitting at a height of 1, a set of blue points sitting at the height of 0, and you must learn a function that captures this relationship. The problem is these data are not linearly separable. Now, what is a linear boundary for 1-dimensional data? Anyone? Saying something? It's just going to be a threshold, right? Now, when in 2 dimensions, it's going to be a line. In 3 dimensions, it's going to be a plane. In 4 dimensions, it's going to be a 3-dimensional hyperplane. In 1 dimension, it's going to be a point. It's going to be a threshold. So a linear decision is going to say, everything to the left of some point must be classified as blue. Everything to the right must be classified as red. Now, can you actually see a linear decision boundary for this example? There's no place where you can actually draw a boundary and say everything to the left should be blue and everything to the right should be red. You have red dots in the blue regions and vice versa, right? Now, instead of trying to draw just a simple linear boundary, you can say, okay, I'm going to go ahead and try to learn something complicated. Something complicated for this data is going to look like this. Now, question A, does this even make sense? It's too detailed. You're sort of following the details of the data and ignoring the fact that perhaps the data are just not fundamentally separable, and the details that you capture may have nothing to do with the underlying reality of the problem. But even assuming that you're happy to do this, let me give you another problem. Suppose my training data are of this kind, where I have several blue and red dots at the same value of x. In this case, how would you learn the function? There's no clear definition for what the function value must be, because I have conflicting training instances. I have some red points at that value of x, and I have some blue points. So what would be a good value for the actual function that you want to plot? Now, let me give you a specific example where I have at a particular value of x, I have 90 instances of red and 10 instances of blue. Then what should I call the value of the function at that x? Should it be 1 because 1 dominates? Or should it be 0.9, indicating that 90% of the instances belong to the class 1? What would you choose? Anyone? Which makes more sense?
1 seems like 0.9.
1 is just the majority value, right? 0.9 gives you a better idea of what really is going on. So what is 0.9 over here? The average is going to give you the posterior probability of 1 given x. So this is more informative. It tells you that whenever I see this x value, 90% of the time the input the y value had y had a value of 1, and 10% of the time y had a value of 0. Now this is more informative, right? But this you understand. Now let me just do something simple. I'm going to perturb the training examples by a tiny amount, 10 raised to minus 17, which is the resolution of your floating point, 32-bit floating point number, right? Now, in this case, let's say all of the red points are off by 10 raised to minus 17 with respect to the blue points. Do you really want to draw this jagged function which says this is red and this is blue? It doesn't make sense, right? You're really within the resolution. I mean, just the fact that we thought the output of 0.9 made sense over here means that we really shouldn't be changing our opinion all that much just because there was a tiny change in the position of the points, right? Intuitively, you see what is going on over here, the argument we are trying to make. So in this case, what must the value of the function be? This is still my training data. The reds are shifted with respect to the blues by 0.000000000001, right? What must the value of y be? What would your best guess be? It still be 0.9 because you're really not making it, it's not such a gigantic distinction, right? So let's change our perspective of the problem. Given the fact now, so where do I decide? Should I say that I'm going to take the average if the difference is 10 raised to minus 17, but I'm not going to take the average when the difference is 10 raised to minus 16? How do we actually make a decision of this kind, take a decision of this kind? Anytime you're sort of taking it upon yourself to draw some kind of hard boundaries, it doesn't make sense. Whatever you do is going to be wrong, right? Let's change our perspective of the problem. At each point, instead of looking at just the training instance, let me draw a small window around that training instance and count what fraction of instances had the value 1 within that small window around that training instance. And I'm going to plot the average value within that window, and the average value is going to be the fraction of training instances which had that value of the fraction of training instances within that window whose y value was 1, right? So as I keep plotting this left to right, what you will find is that this average is basically an approximation of the probability, a posteriori probability of y taking the value 1 when x takes the corresponding value. So this average is simply an approximation of p of y equals 1 given x. And so as you go left to right, as you slide from the blue regions to the red regions, you're going to find that initially the average values are all 0. And then as you move forward, you begin to see some red instances. And so now the average moves off 0. It's going to keep moving up off 0 until you stop seeing any more blue instances. And now the average is going to be strictly 1. And the actual plot you get, this is the function. Now again, we are no longer taking the actual y value that was given to us as part of the training data. We are coming up with a fictitious y value. But this fictitious y value is not strictly fictitious. This y value is giving us the a posteriori probability, or at least our best guess, for the a posteriori probability of y taking the value 1 for that particular value of x. And this function looks very familiar. That's your sigmoid, right? So it turns out that in problems like these, the sigmoid is actually a very good guess for what the a posteriori probability must look like as a function of x. And so what we will do is to try to fit a sigmoid on top of this curve. And the learned sigmoid is going to give you your best guess for the a posteriori probability of y given x. Now the sigmoid we are all familiar with. This is just a standard sigmoid neuron where the inputs have some weights and there's a bias. The bias tells you where the sigmoid takes the value of 0.5, and this function goes from 0 when x is, as if for a positive weights, this function goes from 0 when x is minus infinity and to 1 when x is plus infinity. So this is exactly the curve that we were looking at, right? Now let's go to the two-dimensional case. So we've seen what the one-dimensional case must behave like, in our opinion. Now let's consider the two-dimensional example. Here, this is the figure I showed you earlier. You have some blue dots on the floor on the right-hand side. You have some red dots suspended in the air on the left-hand side. And so clearly I can't draw a nice clean function which just goes from blue to red, right? And something that's jagged and sticking out all over the place doesn't really make sense either, even here. In fact, it makes even less sense over here. And so what we really want is a function of this kind, smooth, going from where as you go from one side of the plane and walk in a particular direction, the function takes a value of 0, and then it sort of slowly increases and goes up to a value of 1. It's a sheet which is kind of folded like so. And this is going to be your logistic function. This is your sigmoid again, except this is over two-dimensional inputs. Now the function itself is not a plane anymore. It's not a line. It's not linear. It's actually a nice curve. But we will claim that this is still a linear classifier. Why is this a linear classifier? Anybody? Regardless of what decision boundary I choose, that is going to be a line. So if I decide that 1 over 1 plus e raised to minus equals constant, and I choose some constant, and I decide that the output is going to be 1 if this value exceeds the constant. And this is my classifier. Then you can work your way back, and you see that this basically says that you want that this resolves to e raised to minus w1 x plus w0 equals log c. This is going to be minus log c, right? 1 plus. Or I can move this and say minus 1. This is just a constant. Sorry, there's no e here. And that's the function of a line, right? So anyway, so this is a linear classifier. Now, how exactly? Now, there's in the case of the one-dimensional example, it was fairly straightforward. I can explain it as saying I go left to right. I use a sliding window. Within each sliding window, within each window, I actually compute the average value of the output and I plot it. And now I can try to fit a sigmoid. Now, once you go beyond one dimensions, that kind of logic doesn't really work. We need some kind of a nice, clean way of figuring out what the parameters of the logistic must be. And so what we will do is we're going to use maximum likelihood estimation. Again, the problem here is a given training data, many xy pairs, and we want to estimate this w0 and w1, which give you the best function to explain the training data. Now, so this function over here goes from 0 to 1. This is the probability of 1, y equals 1, given x. The probability of y equals 0 given x is going to be 1 minus this guy. So it's going to be something that goes that way. That's this blue curve. So probability of y equals 1 given x is the red curve. The probability of y equals, if I use 0 given x, is going to be this blue curve, except for the purpose of estimation, I'm going to change my notation, and I'm going to use a plus 1, minus 1 notation. So y either takes the value of plus 1 or the value of minus 1. So this red curve is the probability of y taking the value plus 1 given x. The blue curve is the probability of y taking the value of minus 1 given x. And you will see the only thing that changes over here is the sign of the exponent. And because the only thing that changes, this is p of y equals 1 given x is 1 over 1 plus e raised to minus wx. P of y equals minus 1 given x equals 1 over 1 plus e raised to plus wx. I can write these together as a single combined equation and say p of y given x equals 1 over 1 plus e raised to minus y times wx. And you can just see that, if I plug in the value of y equals 1, I get this equation. If I plug in the value of y equals minus 1, I get this equation. Straightforward, right? And now once I have this, I can use maximum likelihood estimation. So here is the setup. I have a bunch of training instances, x1, y1, x2, y2, x3, y3, and so on. The x's are vectors, input vectors. Y's are binary. They take the value plus 1 or minus 1. This should be +1 or -1 class values. And so the total probability of the data is going to be the total probability of all of these training instances. And assuming that the training instances are independent of one another, that is going to be the product over all of the training instances of the joint probability of x and y. Now, I can decompose this as the probability of x times the probability of y given x. And we have assumed earlier that the probability of y given x is given by this logistic function. So plugging in the value for the logistic function, you're going to get that the joint probability of the entire training data is given by this term here, which is the product over all of the training instances of the logistic function computed at the training instance times the probability of that corresponding x in the training instance itself. So this is what we will call the likelihood of our training data. The log likelihood of the training data, the log is a monotonic function. That's simply going to be the log of this guy, which is the log summation of the log of px minus, because this is in the denominator, the summation of the log of this denominator term. And maximum likelihood estimation is going to try to maximize this log likelihood. And so it turns now maximizing this log likelihood is the same as minimizing this term, right? Maximizing the negative of this term is the same as minimizing this summation term. That's going to be the same as minimizing this summation term over here. There's no need for us to actually get into the arithmetic of it. The point of this is that this equation is very familiar to you. If you've been training neural networks, this is just your cross entropy loss. The reason I can ignore the first term is that the first term is not a function of the parameters of the network. So maximum likelihood estimation of the logistic function is simply the same as minimizing the cross entropy loss for the perceptron in this case, because you're speaking of a single perceptron, which is a linear classifier, right? Can't be solved directly, so you're going to need gradient descent. Now hold this thought. If you've all taken 701 or 601, there was nothing particularly novel about what we spoke of so far. This is just trying to estimate a logistic regression function. Standard sigmoid. I give you a bunch of training data. You can compute the cross entropy between the output of the sigmoid and the target output and train the sigmoid, right? But now let's go to the more complicated function where I am trying to train a classifier for data of this kind. This function is not a linear classifier anymore, right? And this fuzzy function is kind of a complex case. So first let's go and look at what happens for the simple case where the data are actually perfectly separable, right? If the data are perfectly separable, what I mean by separable is that the red region, the double pentagon, is clearly demarcated from the blue region. Any data point that falls in the double pentagon has an output value 1. Anything that falls in the outside it has an output value 0, right? So if I do this, and now let's assume that I have a network. We've seen this problem before. We've seen this problem in lecture 2. So let's assume that I have a network which is capable of perfectly classifying this data, provided the parameter values are set properly. So we've seen this. In this case, each pentagon can be computed using something of this kind, where you have 5 units capturing the 5 lines, and then something that combines those 5. The second pentagon can be captured using another version of the same 5 first layer neuron network. And then these 2 pentagons can be combined to give you the final overall classification, right? This we have seen. And if this is trained properly, if the parameters are set properly, then this should just work. But then here's the crazy bit. This final perceptron at the end, this is still a linear classifier. We are still using just the threshold units or the sigmoids, right? So if the final output is a linear classifier, and you're classifying, and it's doing a perfect job of classifying whether these inputs are red or blue, what does it tell us about what is happening out here? Now, the only way the final perceptron can do a perfect job of this classification is if these features are linearly separable into red and blue, because the final perceptron is a linear classifier, right? What does this mean about the rest of the network? So for perfect classification, the output of the penultimate layer must be linearly separable, right? Because that is how perceptrons actually operate. That means the rest of this network has only one job in life. It takes this complicated looking input and somehow manipulates it such that they've been separated out and now the classes are linearly separable. So the network, in fact, has two components, which has the first component is this feature computation module, so to speak, which works on the input, modifies it and modifies it and modifies it until the classes are linearly separable. And then finally a classifier which actually operates on these linearly separable features and actually affects the classification. But then once you have this realization, you have, there is more insight to be had in the problem. If I give you linearly separable data, what is the best kind of classifier that you can actually plug on it? Do you always want to be using a logistic regression? Or would you, if you were conservative, what would you be using? You'd be using something like a support vector machine, which maximizes the margin to the nearest point, right? So which means that in reality, this final thing doesn't even have to be a standard perceptron. This could be a support vector machine, right? So in fact, it turns out that for binary classification, if you built your neural network and the final perceptron were not just a standard logistic, but was in fact a support vector machine, you might get more generalizable classifiers than if you were using a standard MLP. Now, this is not something that pops out at you the moment you look at an MLP, right? The fact that what the MLP is doing is a two-stage process which converts the input into linearly separable features and then plugs a linear classifier on top. That's not something that immediately pops out at you, but the moment it does, then you begin seeing these other alternatives. That if I thought of this as some mechanism for generating linearly separable features from my entangled features and then putting a classifier on top, then the possibilities of how you do this actually expand greatly. Now, what happens if my network is not just a sufficient network? So for this data to be separable, I need this network, right? If I got rid of one or more of the connections, there's no way that this network can actually classify this input anymore. This structure is not sufficient. What would happen in this scenario? Or what if I had too many parameters? Something like this, over-parameterized. What would happen in this scenario? So here is the interesting result. There was actually a very nice talk yesterday by Yunji Lee from Princeton, who actually talks specifically about problems of this kind. And what he shows is that if you took a sufficient network of this kind and added a whole bunch of extra parameters on it, just blew up the size of the network, such that the expanded network included as a subcomponent the optimally sized network, then you're guaranteed that if you learn this with sufficient amount of data, this network will actually learn the correct function. It's not merely going to overfit your training data. So it's a very pretty result. That even if the amount of training data is lesser than the number of parameters in the network, it's actually going to learn to generalize and give you the correct function. But then, so that intuition sort of falls out differently also from what we've been talking about. What exactly would the network be doing if if the structure were either insufficient or over-parameterized. It turns out that the final classifier is still a linear classifier. The final classifier is still being forced to perform linear classification. If you're using a logistic, it's not going to be able to do a perfect job, but it is going to be able to try to come up with a guess for the a posteriori probability of P of y equals 1 given x, right? So in other words, what will happen is that this network, although it cannot separate the features out into linearly separable groups, it is going to try to make them as linearly separable as possible. And once you get past that point, then the final classifier can actually operate on the features that have been extracted and try to learn something from it, right? So it will fail to separate, but you're still going to try to. We have some problems with audio, right? So it's still going to try to classify. The first portion of the network is going to try to generate linearly separable features, and the final classifier is going to try to separate them. But the whole process, the whole decomposition, the early portion of the network is trying to separate these features out into separable regions, still holds, right? Now, so what will happen? So here is what we can think of, and how we can think of it in mathematical terms. Y out is there's a minus messing over here, but it's basically a logistic function of the features derived by this function f of x, which operates on x. And f of x is some nonlinear function that tries to make the input as linearly separable as possible. So it tries to make the classes maximally linearly separable. So here's the story so far. A classification MLP actually comprises two components. There's the lower portion, which the feature extraction network that converts the inputs into linearly separable features. It sort of modifies the inputs such that the classes are linearly separable. And then there's a final linear classifier that operates on these linearly separable features such that they can be classified. So if you were trying to do, for example, now once you actually realize that, you realize you can modify the final unit and have any kind of linear classifier. You could have a logistic regression, a perceptron, or you could have a support vector machine. And if you wanted to use a support vector machine, how would that work? There are different ways of doing it. You could first train the MLP with a standard perceptron. You can detach the feature extraction module, because you know now that the feature extraction module has actually managed to convert the features into something that's linearly separable. Then you can maybe train a more conservative support vector machine on the features that have been derived. And that should, in principle, work at least as well as simply having a perceptron. Or you could plug in an SVM at the end and just jointly train the whole thing to try to make the such that they are jointly optimal for classification. But regardless, you get the idea that once I think of this as a feature extraction module that generates linearly separable features and a linear classifier, then the perspective to what you can actually do with structures such as these changes. Now, how about the lower layers? What are the lower layers doing? I just gave you this big round box, this big rectangular box around the lower portion of the network, and this is a feature extractor. It's going to work on the input and somehow going to generate linearly separable features, right? But this lower network typically has many layers in it as well. What do those layers do? How do they modify the input? Because something's happening. You have the input, each layer is modifying the input in some manner until they are finally linearly separable. And then the linear classifier can operate on it, right? Now, it's not very clear exactly how the lower layers modify the data. If you actually see anyone trying to interpret individual neurons in this network, they're kind of off the mark. You really cannot do it because the network, among other things, the features that you extract are rotation invariant and affine transformation invariant. So you can't identify the purpose of individual neurons in any particular layer, but you can get some kind of an idea of how all of the neurons, what all of the neurons do as a group when they process the data through the layers. And so one particularly interesting and possibly intuitive hypothesis is the so-called manifold hypothesis, which says that for separable classes, for example, like this guy, where the classes are separable, what is really happening is that there is some inherent manifold, some curved surface in some high dimensional space where the data are linearly separable. And what this box is doing is sort of taking this curved manifold in the high dimensional space and sort of incrementally stretching it out such that this curved manifold becomes planar. And then now you can actually use a linear classifier on the plane. Now, if this indeed were the case, the layers would be sequentially straightening the data manifold. Does that really happen? Let's take a look. Here's a synthetic example. So we are trying to build a classifier on two-dimensional data. The data is of this kind. The axes are squished. There's a circular or squished vertically. So the decision boundary is circular. And you want everything inside the blue region to be classified as 1, everything in the red region to be classified as a 0. This is a very simple network. It has 2 dimensions. Then you have a 2, 3, 1. So the second, it has only one hidden layer. And the one hidden layer has a tanh activation. So after the first hidden layer, now observe what has happened. We have actually said, now you can think about what is happening. If I have a circle and I have in a plane and I want to classify the circle from against the rest of the circle, then the correct way to think about it is that if these two together represent a projection in onto 2 dimensions of something in 3 dimensions, where the circle is raised off and the rest of it are on the plane. And now in those 3 dimensions, I can actually draw a linear classifier which just slices the circle away from the plane, right? Is that really what is happening over here? So this guy, there are 3 hidden neurons in the single hidden layer, and this figure here is plotting the output of the 3 hidden neurons for each of the training instances. Now, because the training instances lie on a plane, 2-dimensional plane, even in the 3-dimensional space, they're going to lie on some kind of a continuous sheet. And you can see what exactly is happening, right? So this is the 2-dimensional output. When I compute the affine combination, 3-dimensional affine combination, which is Wx plus B, this 2-dimensional output is going to end up looking like some sheet in 3 dimensions. And then I put this to a tanh activation, it's going to end up looking like this. Then the final neuron is a single neuron, right? So the final neuron is going to be computing again an affine combination of the features over here, but it's a scalar. It takes a single value. So if I plot that, it's going to take only it's a scalar value. The second dimension is kind of spurious over here. They're all going to lie on a line, and they're color coded, right? So when I initialize this training, this is the input with the initial values of W and B. This is what this plane is converted to. This is the output of the activation. And then at the second layer, the affine combination looks like, so you have red on both ends and blue in the center, right? And there's really no way for me to draw a decision boundary on this. Now let's actually try to go through a training process if I can and see what happens. So it's very interesting to see what is happening. The plane is kind of rotated till it finds some specific skew where applying a tan H activation separates the blue from the red, such that after if you apply an affine combination to these guys, now the affine combination of the activation transformed inputs look like this, where the reds are very clearly separated from the blues. And now on the reds and then now on this figure, I can actually apply a single threshold which separates out the blue region from the red region, right? But the point is, this whole training process has sort of taken these this two-dimensional data where the classes are not linearly separable. And as it operates on it, it's sort of converted them into something that's linearly separable. Now you can actually apply a threshold. You can also see the fact that the training has not been perfect. So you have a little bit of red out here, right? And this decision boundary is not exactly circular, it's kind of skewed. But if I were to rerun this experiment a dozen times, more often than not, it will actually find, just using this minimal network that has only 3 hidden neurons, it will actually find an almost perfectly circular decision boundary. So you see what's happening, right? Now this is a simple two-dimensional case. Let's look at something more realistic. This is CIFAR 10. Yeah. And you have data from many different classes. And we've taken this data. We've initialized a network in this case with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 layers. And we've projected the output of each of the layers down to 2 dimensions using principal component analysis for you to, and the color coded the various classes. And when you start off, you can see that the classes are all mixed up, right? Initially. But then and in every layer, the classes are mixed up. But then what happens as you actually train the network? As you train the network, you can see that, wait, why did this work? That was too fast. But you can actually see what is happening over here. As it goes through the layers, this is the accuracy as a function of iterations. And the first layer, the classes are still kind of mixed up. The second layer, the classes become a little more linearly separable. As you go through them, eventually, even by the time you get to maybe the 1, 2, 3, 4, 5, 6, the 7th layer, the classes are nicely linearly separable. And something interesting happens if you keep adding layers to this, which is actually the 10th layer. The 11th and the 12th layer actually increase the separation between the classes in this particular example. But what is really happening is that the classes are becoming increasingly linearly separable as you go through the layers until they are sufficiently linearly separable that a linear classifier can actually separate the classes. Now, in 2 dimensions, it's not so clear. Let me do this in 3 dimensions. It's still the same network. It's still the same training, except that I've used principal component analysis to project this down to 3 dimensions for visualization. And you can see exactly how the whole thing behaves, right? Till 1, 2, 3, 4, 5, 6. The 7th layer, they actually sort of begin to get linearly separable. And then subsequently, they are being separated within the plane, but they're also being separated. The different classes are being put in different planes. But again, the point that is coming across is that the task that the feature computation portion of the network is performing is to make the classes linearly separable. And the linear separability increases as you go through the layers. Now, that was for data that are linearly separable. But then we started off saying the data are not going to be linearly separable, right? When the data are not linearly separable, this is a more typical setting. What really happens? Now, the feature extraction layer, it's the same concept still holds, but now the feature extraction layer transforms the data such that the posterior probability computed by this guy can be properly modeled by a logistic. So you're really fitting a statistical model. We've thought of the neural network as some arbitrary function, a classifier, but what the network really is is a statistical model. It is learning to compute the posterior probabilities of the classes. And what you get at the output is indeed the posterior probability of the classes. It's not a hack, it's not an approximation. This is really maximum likelihood training. It's in fact the same maximum likelihood training that you perform when you're training your simple perceptron, the simple logistic function. So the reason I actually went through the process of explaining how training a logistic function is the same as minimizing the cross entropy carries over here. In fact, when you're minimizing the cross entropy, you're learning a more complicated model, but the model is learning to compute the posterior probability where the feature extraction layer transforms the data such that the final neuron can now compute the posterior probability using a logistic function, and the output logistic actually computes the posterior probability of the class. So the output of the network is going to be P of y given x, and for multi-class networks it's actually going to be a vector of posterior probabilities because that's what the softmax actually gives you. Questions? Yes?
How do neural networks perform better than SVM, which also perform like a transformation using the kernel tree?
You're fixing the kernel, right? If you don't have the right kernel, you're not really going to get anything. And for most data, you don't really know what the ideal kernel is. So you're hoping that whatever kernel you choose is going to separate your data. That's highly unlikely to happen. Here it learns the process. It actually learns how to separate the data. And now you can actually perform the training, right? No questions? None on Piazza? Okay. So everything I said might be wrong, right? I might have just spoken for an hour and not told you anything useful. There's this very nice book called Illusions by a guy called Richard Bach, which has 99 pages of a very philosophical story, and the final one says everything in this book might be wrong. So now there's no such thing as inseparable classes. The odds that you will get true training instances with exactly the same x are practically zero. So what you're going to get is something of this kind, and there's nothing stopping you from plugging a function of this kind on your data. This function is particularly hideous and ugly, right? And a sufficiently detailed architecture can separate nearly any arrangement of points. So the correctness of the intuitions I gave you are subject to various parameters like regularization, detail of the network, training paradigm, convergence, etc. But one thing I learned yesterday from the talk yesterday is that even this statement is kind of wrong. In that if the larger network actually includes the smaller network, the smaller optimal network for the data, then you're almost certainly going to find a solution that generalizes correctly. If it doesn't, then all bets are off. So, changing gears, we've been talking about what the network as a classifier does. When I'm trying to learn a network which performs classification, what is happening is that it's all governed by the final layer, which typically is a softmax or a logistic. A softmax or a logistic actually computes posterior probabilities for the classes for data that are almost linearly separable. So the entire model comprises two parts. The first part actually separates the features, and the final layer computes the posterior probabilities. And what we are actually performing is the training of maximum likelihood training. But then here's a different perspective, right? We've seen what the network learns here. What happens over here? Now, let's take several steps back and go to class number 2 again. Recall the basic perceptron. Remember what we spoke of when we were using a threshold activation. The network looks at a weighted combination of the inputs. If it exceeds a threshold, it fires. Each unit looks at a weighted combination of its inputs. If that exceeds a threshold, it fires, otherwise it doesn't, right? So one way to look at it is to say that you're looking at the inner product between the weights and the input. And if the inner product basically measures the cosine of the angle between the pattern of the weights and the pattern of the inputs. And if this angle is smaller than some threshold, the unit is going to fire, otherwise it doesn't. We've seen this at least twice before. And so what this means is that each unit is really some kind of a correlation filter. So if your weights pattern had this structure, then what you're really doing is computing the correlation between the input and the pattern of weights. And if this correlation exceeds a threshold, the unit is going to fire, otherwise it doesn't. More typically, if you're using something like a softmax or a logistic or any other activation, it's sort of the output is giving you some function of the correlation between the input and the weights. So if you were trying to perform something like of this kind, where you look at a collection of inputs, you look at a collection of features and you're trying to make some guess about the input. So here's an example. The input is a grid of pixel values, and the network must decide if this grid of pixel values represents a valid digit or not. Then what you would expect is that the lowest layers, because all of the neurons are eventually correlation filters. So what you would expect is that the neurons in the lowest layer will learn to detect individual features in the input that are characteristic of digits or characteristic of something being not a digit. So you might find, for example, that one of them learns to detect little horizontal bars, another one tries to detect little vertical bars on the side, and so on. And each of these detects a feature from the input. The next layer actually combines these features to compose larger patterns. And then the final guy, maybe each of these guys actually learns to detect one of the 10 possible digits. And the final guy just decides, has any of these 10 guys fired or not? But the key component over here is that this lowest layer actually captures features. And which feature has been captured is represented by the weights. That means I could technically go back and say, okay, this neuron is trying to detect small vertical bars. So if this neuron has fired, I know that the input has a small vertical bar. So based on the outputs of these neurons, I could go back and try to reconstruct the input, right? I could just go there and I could plot a little grid, and I say, neuron 1 has fired, so I'm going to fill this up. Neuron 3 has fired, so I'm going to fill this up. Neuron 5 has fired, so I'm going to fill this up. Neuron 6 has fired, so I'm going to fill this up. And based on the firing patterns of the neurons and knowledge of what the weights are, because the weights tell me what patterns it's looking for, I could reconstruct the input, right? So would I get a perfect reconstruction of the input doing something of this kind? So here's what the actual structure is going to look like. Here are the neurons. These are the weights. These neurons fire if the patterns represented by these weights are discovered. But when the neuron fires, how do I fill up the reconstruction? I fill up the reconstruction according to the weights themselves. So if the first neuron was looking for something on top, when it fires, I'm going to fill up the top region of the picture, right? So in other words, the reconstruction is done by the transpose of the weights. If a neuron fires, the weights coming in are going to be the same as the weights going out, right? So if I did this, I could try to reconstruct the input. You're going to reconstruct the detected inputs. Does this mean it's actually going to reconstruct any input at all? In this particular problem, no, because the network has been optimized to recognize digits. So if I started off with this guy, and then I threw away everything on top, and then try to reconstruct stuff based only on what features this layer has detected, because the network is optimized to recognize digits, it's only going to retain distinctly digit-like are obviously not digit-like features. The rest are irrelevant. They're going to be lost. Right? So you get what I'm talking about. Let me try to make this more explicit. Let me try to build a network that actually learns to detect patterns that can be used to actually reconstruct the input. So this is what we will call an autoencoder. It's going to encode the input. So this is a neural network that's trained to predict the input itself. It has two parts. This is the encoder, which learns to detect all the most significant patterns in the signals, and then the decoder, which recomposes the input from these patterns. Right? Let's try to analyze these guys. Let's take the simplest possible autoencoder, and the simplest possible autoencoder has only one neuron, right? So specifically, to make it even simpler, I'm going to get rid of the nonlinearity in the neuron, and I'm going to assume that it has a linear activation. So in this case, X goes in, this guy computes some weighted combination of the inputs. Based on these weighted combination of the inputs, it tries to reconstruct the input itself. What is it actually going to learn? It's very simple. The output of this neuron is simply going to be W times X. The reconstruction is going to be W transpose times the output of this neuron, which is W transpose times W times X. The error that you're trying to minimize is the error between the desired output, which is the input itself, and the actual output, X hat, which is going to be W transpose times W times X. So this guy is the error that you would try to minimize in this case. If I expand it out, it's just this term. And what is this minimization? This is just principal component analysis. So basically, if I had a single neuron which had a linear activation and it was trying to reconstruct the output, what you're really going to get is principal component analysis, right? So in this case, what the autoencoder has done is to find the direction of maximum energy in the input, or if the input collection of inputs is zero mean, it's going to find the direction of maximum variance in the input. And so the direction of maximum energy is going to be this guy. And so here's the interesting thing. Regardless, so the output over here is going to be some scaling of this weight, right? So the output is always going to fall on a line or a plane, regardless of the input. So what happens over here is, if I just took the decoder portion of this and varied, the decoder actually operates on some z, which is output by this neuron. So if I varied the z from minus infinity to infinity, the output is always going to lie on the blue line, no matter what the value of z is. And this in turn means that regardless of where the input was, the input can be any of these dots, the output is always going to lie on the same line. Because the output is always going to be some scaling of this weight vector W. Right? Now, so what this means is that regardless of the input, the output is going to be aligned. Now, in the example network that I gave you, which is not a network, it's a single neuron, the reconstruction weights were the same as the input weights. But even if I separated these two guys, if I call this U and I call this W and the two are separate, you're still going to learn to reconstruct outputs which only fall on a single line, which is some scaling of this vector U. And more to the point, you're always going to find the principal direction, the direction of maximum energy in the inputs. And the outputs that you get, regardless of the input, are always going to fall on this line. Right? Does that make sense to everybody? Right? Now, let me go from a single hidden neuron to many hidden neurons. What happens in this case? So in this case, I have a collection of hidden neurons. the output is going to be a vector y, which is some w times x. I'm still assuming that it's a linear activation. There are no nonlinear activations. And anytime a feature is discovered, I'm going to put that feature back to try to reconstruct the input, right? So the output is going to be w transpose times y, which is w transpose wx. The error I'm minimizing is the squared error between the output and the desired output, which is the input itself. If I learn my parameters to minimize this guy, this is a very familiar equation. This is just principal component analysis. So even if I have more than one neuron, if I am trying to auto-encode and my activations are linear, what the network will end up learning is principal component analysis. It's not going to find the principal directions, it's going to find the principal plane. And so this has, it's going to find, and this is going to happen even if these W's are different, if these weights are different from these weights. And here's what happens. Regardless of the input, the output has to be some combination of these weights. So regardless of the input, the output is always going to lie on this principal plane, right? This is with linear activations. So terminology, again, I'm thinking of this in terms of two sets of two components. The first is the encoder, which works on the inputs and gets some representation, latent representation, and the decoder, which reconstructs something from this latent representation. And what we found is that the output is always going to lie on the surface that the decoder is able to reconstruct, and it cannot reconstruct anything else. And where on the surface you end up depends on how the encoder actually places you there. And if the network has been learned properly with linear activations, this is going to learn the principal surface for the input, right? What if my neurons have nonlinear activations? We've been speaking of linear activations. I suddenly went from linear activations to nonlinear activations. What happens in this case? When the hidden layer has nonlinear activation, instead of trying to find the principal plane or the principal line on which most of the energy lies, it's now going to find a principal manifold, which is some kind of a curve, a curved surface. So here, if I had a nonlinear activation over here, and this were my training data, the encoder is going to the decoder is going to be able to reconstruct this black curve, and the encoder learns where on this which point of the black curve any training instance is closest to. So the entire structure learns the structure of the entire network, learns the structure of the underlying data, and actually learns the principal manifolds. So what this network is doing is that it's actually performing nonlinear principal component analysis. And now you can think of what happens with deep networks. If I have a deep network, then the encoder and the decoder, now the two don't even need to have the same structure. I can take any deep network, which is an autoencoder, and think of some portion as an encoder and something else as a decoder. The encoder is learning a manifold, and the decoder is learning to reconstruct on this manifold. And you're learning more and more complicated manifolds for the data, right? And the deeper the network is, the more complicated the shape of the manifold that it learns. Meaning the more complicated the structure of the data, the structure that the data can have, that the network will be able to learn. So I have a couple of examples. Go back to two-dimensional examples. Now look at this guy. There's a very implicit structure over here. The data lie approximately on a spiral, right? If I were to think of a single number and a decoder to represent this data, what would that single number be? I'm going to give some position on the spiral, call some position on the spiral an origin. And the only thing I need to know is where on the spiral the data is, which means that I can start from here and I can compute the length along the spiral. And so long as I give you that z position on the spiral, I should be able to give you a pretty good guess of where the data lies, right? And it turns out that if I actually train my network properly, this is exactly what it learns. Here, all of the training data each training data gives you a specific z value. So here are the reconstructed values for all of the training data for this spiral, and you can see that it actually learns the underlying spiral. It learns the structure of the data, right? Now, does this generalize? That's a different question. We'll actually deal with this question much in a few more classes when we speak of variational autoencoders. But this training data had some scatter, and for all of these training data points, for each training data point, I got some z value, which is the output of the encoder. And the encoder has only one dimension, because one dimension completely specifies everything about the data. If the decoder is able to reconstruct a spiral, I only need the location on the spiral, right? But say on my training data, it learns to produce z values between 0 and 1. What would happen if I gave a value of 1.1 to the decoder, something that's not seen in the training data? Now, if it's done a good job of learning the structure, it should continue the spiral, right? Does that really happen? It doesn't really continue the spiral. It turns out it does something bizarre like this. In fact, it turns out that it hasn't even really learned the spiral. What it has learned is the structure, right? So it learns something about the structure of the training data itself. It does learn the manifold, but not in the nice, clean manner that you would like it to learn. Here's another example. This is a sinusoid. And this is a noisy sinusoid. If I just use the same encoder-decoder structure, then here are the reconstructed values for the training data. Every training instance has some z value. Here the z's have gone from just to 0 to 6, I believe. What happens if I let the z value go beyond 6 or before 1? Here's how it reconstructs it. It just plots a straight line, right? So in other words, it's learned the structure of the training data, but not in a generalizable manner. So this goes back to our original statement that these systems are actually universal approximators, but they are universal approximators for the data that they see. They're really not very good at going beyond the data that they have seen. And you need additional constraints, right? But anyway, for a little bit of fun stuff, just even the fact that they can actually learn to encode and decode the structure of the data, we can put this to use. Now, when the hidden representation is of lower dimensionality than the input, we're going to call this a bottleneck structure. We've seen that it performs nonlinear PCA. It learns the manifold for the data if it's properly trained. Now, but here's the fun bit. The decoder can only generate data on the learned manifold, right? So here, for example, if I'm within this region, anytime I give you a new z value within 0 to 6, whatever it generates is going to only lie on the sinusoid, or it's not going to lie off the sinusoid, right? And practically, what does this mean? It means that the decoder is an excellent generator of the distribution of the training data. And any values applied to this, if I give you any value, once I train this and I give you this decoder, and I give you any value for this latent layer, whatever it produces is going to be within the manifold of the training data that it has seen. So here, for example, so what this means is that the decoder is a source-specific generative dictionary. I can just take this decoder portion of the network, and regardless of what value I give it, what it produces is going to be something that looks like it could belong to the distribution of the source. And so let me try some fun examples. Here, we've actually used an autoencoder to learn to autoencode little bits of music. Saxophone, music from the saxophone in this case. And then after having encoded it, I just took off the decoder, and I'm going to excite this decoder with different patterns. And what you will see, and then of course it's going to produce some spectrogram which I can synthesize as sound, and here's what you're going to get. This is for a saxophone. With different inputs, it produces different sounds. It doesn't produce white noise. It doesn't produce gobbledygook. It actually produces something that's musical. It produces something that sounds somewhat like a saxophone. Not a single note, but something that, a bunch of sass that could potentially have come from a saxophone. Now, just to convince you that it's not magic, that it's not some generic musical sound, here's another one where we train it from a clarinet. Very distinctly clarinet sounds, right? So you can see what it's actually learning. It's learning to generate stuff on the manifold of the data that it's actually seen, which, if you think about it, is very impressive, right? So, and now having shown this, I'm going to just spend a few minutes showing you a very cute little application of how I can put this to use. I'm going to try to separate mixed up sounds, right? The idea is, given a mixed sound from multiple sources, I'm going to try to separate out the sources. I'm going to use something called a dictionary-based approach, where the basic idea is to learn a dictionary of building blocks for each sound source. So let's say somebody is playing a guitar and somebody is playing the drums side by side, and I got a recording which includes the guitar on the drums. I want to separate out the guitar from the drums, right? I'm going to try to learn a dictionary of building blocks, something that can only generate guitar sounds. So, and all signals that are by the source are basically, I'm going to assume that I have this machine, this decoder, and anytime it produces anything, it's only going to produce guitar sounds. Pretty much anything that it composes is going to be a guitar. I do the same thing for the drums. I'm going to learn a dictionary that can only generate drums. And then, when I have some mixed signal, I'm going to try to decompose it and say, how do I separate this into something that could have been, how do I combine what the outputs of the dictionary, the guitar dictionary, and the drums dictionary to best produce the mixed sound. Now, this conceptually sounds kind of slightly wacky, but it's very easy when you actually think of it in neural network terms. So once I do that, I can sort of separate the guitar and the music and the drum sound out, and that's going to be my guitar and my drums. So let's take a look at how I would do this with my simple autoencoder. I have a collection of, in this case, guitar sounds. I train an autoencoder. I have a collection of drum sounds. I train an autoencoder. Then I'm going to throw away the lower portions of the drum sounds and the lower portions of the autoencoder for the guitar and the lower portion of the autoencoder for the drum. Now, what we have seen is that regardless of how I excite this guy is only going to produce guitar-like sounds, right? Regardless of how I excite this guy is only going to produce drum-like sounds. So now if I give you a mixed sound which includes guitars and drums, all I have to do is to decide how was this guy excited and how was this guy excited, so that when I added them up, I got a mixture of a guitar and a drum. And how exactly can I do this? Backprop. I just stick my guitar out here, my mixed recording out here, and typically you use backprop to learn the parameters of the network, right? But there's nothing magical about the parameters of the network. You can actually use backprop to go back and learn what the input of the network must be to generate a specific output if you fix the parameters of the network. And so here we're going to use backprop to learn what these inputs must be to reconstruct this output. And then once you've done that, I know what this input is once I've estimated it. So the output of this guy must be my guitar, the output of this guy must be my drum, and the two have been added up to give me what I really heard, right? So let's try this little example now. Here I'm going to try to separate music. It's got two instruments. Anybody recognize the instruments? Mellon and oboe. Yeah. So we had a collection of, so these were the two. So these are the original that I mixed up. I've taken a collection of violin and oboe recordings and learned my user and trained an autoencoder and learned the decoders for the violin and the oboe. And now I'm going to use those to try to compose the mixed sound that you just heard And then I'm going to figure out what each of them generated in order to compose this guy. And that's simply, and what did each of them generate? What does the separated sounds sound like? Pretty impressive, right? The fact that it actually learns these, but should give you a pretty good idea of how what the network has actually learned. It has learned the manifold of the data. And at this point, the only thing it is able to generate is something that lies on the manifold. And in this case, I'm actually using that to separate out these two sounds. Anyway, I'll close here. So the story so far for the day: classification networks learn to predict a posteriori probabilities of classes. The network until the final layer is a feature extractor that converts the input data to be almost linearly separable. And the final layer is a classifier or a predictor that operates on these linearly separable data. But more generally, you can think of the rest of the network as learning some kind of a manifold structure for the data itself, something that you can actually put to good use in many different applications, like transfer learning. We've seen that when you were doing your homework too. What happened was that the feature representation portion of the network learned how to represent faces. Now you could use it for verification. Or in this case, in the second case, where the feature extraction portion of the network learned the manifold for different musical instruments. So now when I give you a mixed recording, I'm able to actually separate the two, because I can tell you how these things had to be, what these networks should have generated in order to compose the final output. Right? So we'll stop right here, and we'll continue in the next class with half-field networks. Right? Thank you.